All right, we have a rare treat today. You can see my chair. I'm actually sitting down, and it's a different day from the rest of the videos. I usually do all the videos for a section in a single day, but I had plans yesterday and it was a Sunday. So we're gonna do some homework problems, starting with 371. Let's see if I remember how to do anything with improper integrals a day later. And yes, that's a joke. Determine whether the improper integrals converge or diverge. If possible, determine the value of the integrals that converge. So basically, find what these equal. If they're infinity, then say they diverge. Because remember, converge means it's a number, basically. It means the limit exists. And diverge means the limit doesn't exist. And remember that a limit equaling infinity still counts as not existing. Writing infinity just is not an actual value of the limit. It's an explanation on how the limit doesn't exist. All right, so 371 is integral from 3 to 5 of 5 over x minus 4 squared. Okay, so remember, we cannot just use the fundamental theorem of calculus because this is not continuous on the interval from 3 to 5. And in fact, I want to show this. I have a little bit of extra time. Feel free to skip through this part if you're not curious about what happens. But let's say this is going to be wrong. Let's say I forgot about improper integrals. Well, I could do a u substitution to get the antiderivative of this. Would be 5 over x minus 4 with a negative in front from 3 to 5. And if I didn't know anything about improper integrals, I could get 5 over 1 minus a negative 5 over negative 1. You get negative 5 minus negative 5, and get that this integral is negative 10 if I did this correctly. Hold on. I mean, if I did this I'm doing it incorrectly, but I want to correctly do it incorrectly. Okay, so if we look at this, because I want to make sure that this is an error from the right place. Okay, so do a u substitution. Du is the same as dx. Add a power and divide by that power just makes it negative. Plug in 5, subtract, it's negative. Plug in 3. Yeah, so right off the bat, if you forget about improper integrals on this problem, you should notice, because this is 5 vertically stretches it, x minus 4 moves it 4 units to the right. This is what this function looks like. If your integral, this is actually very similar to one of the ones we were looking at in the lecture videos. If this net signed area is negative, we got a real problem. So don't forget about improper integrals. Wait, I don't need to erase that. Fundamental theorem of calculus only works on continuous functions. This function's not continuous on the interval from 3 to 5. We have to split it up. Integral from 3 to 4, I'm going to take this 5 out in front. Plus 5 times integral from 4 to 5 of 1 over x minus 4 squared dx. Okay, and then again, we set it up with the limits. It's a little tedious, but it's okay. It's going to be 5 times the limit as a goes to 4 from the left. We always approach from the inside of the interval of the integral from 3 to 4, sorry, from 3 to a. Undo, I say, undo. Of 1 over x minus 4 squared dx plus 5 times the limit as b goes to 4 from the right. That's the inside of this interval. Integral from b to 5 of 1 over x minus 4 squared dx. And then we can go off to the side and calculate this antiderivative. This is the antiderivative of x minus 4 squared dx with a negative in front of the 2. All right, and we can do a u substitution. Let u be x minus 4, so du is dx. And this gives us the antiderivative of just u to the negative 2, du. Add an exponent and divide by that exponent. We get negative 1 over u plus c, which is negative 1 over x minus 4 plus c. Is that antiderivative? Great. Also, again, it's kind of hard to see it. It's a negative and then a fraction bar. So this becomes 5 times the limit as a goes to 4 from the left of its antiderivative, which is negative 1 over x minus 4. We don't need the plus c. From 3 to a. Plus 5 times the limit as b goes to 4 from the right of that same antiderivative from b to 5. 5 times the limit as a goes to 4 from the left. When we plug in a, we get 1 over a minus 4. We subtract when we plug in 3. Subtracting a negative is adding a positive. 3 minus 4 like so. Plus 5 times the limit as b goes to 4 from the right of negative 1 over 5 minus 4 minus a negative is plus 1 over b minus 4. And we have to look at these limits. So as a is getting close to 4. So first off, if a equals 4, we get 1 over 0. If a equals 4, 1 over 0, it basically corresponds to some kind of infinity. Is it positive infinity or negative infinity? And it might help to have this negative in front, kind of up to you, whether you want to look at this piece or the whole piece. For me, it's easier to look at this piece. So we're going to have some kind of infinity. It's a one-sided limit, so we don't have to worry about two-sided disagreeing. If we have 3.9, do we have positive or negative? You're going to have a negative denominator. Oh, 3.99 still going to be negative. If a is less than 4, and it always will be because a is approaching 4 from the left, you can plug in some numbers to really see what's happening here too. You can quickly tell whether it's positive or negative infinity. We're always less than 4, so when you subtract 4, we're going to get negative. This part is going to negative infinity. Means this part is going to positive infinity. And I realize that this question is not even necessary because we know it's going to some kind of infinity. So specifically, also, we know that this area will not be negative infinity because the net signed area is the integral. So we all know we have positive. Lots of things that we can do. As soon as we see this, we're done. We don't have to worry about this. We already know it diverges. This integral diverges to positive infinity. And again, if you want to write that in parentheses, positive infinity, that's great. You don't have to. All the problem wanted is, does it diverge or converge? So even if this over here is a number, which it's not, but even if it were just a number, it wouldn't matter. Doesn't matter whether this second integral is infinity, negative infinity, 0, 5. Even if it's positive infinity plus negative infinity, doesn't matter. If one of them diverges, the whole thing diverges. Next up, 372. Great. Determine the convergence of each of the following integrals by comparison with the given integral. If the integral converges, then evaluate. So it's a little different than the lecture problems. So we're comparing integral from 1 to infinity. Where is it? Of dx over x squared plus 4x. And we're comparing it, the integral from 1 to infinity of x squared. Dang it. Why did I say dang it? Because look at the wording. If it converges, then we have to actually evaluate it. If it diverges, we're done. So I said, dang it, because I know it's going to converge already. Just because I have done a lot of integrals and I recognize that this integral is going to converge. So we still have to prove it. Let's still use the comparison theorem. All right, what's the relationship between these two functions? If x is greater than or equal to 1, and we know it is, because x is on this interval, what happens to our denominator? Well, if x is at least 1, then, oops, let's stay in the same color. then x squared plus 4x is bigger than, strictly bigger than in this case, but we can write bigger than or equal to if we want. This is true, right? We're only dealing with positive numbers, so if I add 4 times a positive number, we get bigger. So that means the denominator gets bigger, and if the denominator gets bigger, that means the whole fraction gets smaller. So if this is our f, and that's our g, g is the bigger one with the notation that we used from our video. F is less than g, and we know that g converges, then f converges. So let's look at g. Okay. The integral from 1, well, we need a limit. B goes to infinity. You can use whatever letter you want. Of x to the negative 2 dx is the limit as b goes to infinity of add a power, divide by that power from 1 to b. So that's going to be negative 1 over b minus a negative 1 over 1. Well, as b goes to infinity, this goes to 0. This whole infinite area is just 1. Wow. Okay. So, by our comparison theorem, since f of x is less than or equal to g of x on this interval, this proves the integral from 1 to infinity of dx over x squared plus 4x converges. That's how we use the comparison theorem. Show that f is less than or equal to g. Whoa, hit the wrong button, which means I can't undo the big circle. Show that f is less than or equal to g. And then if g converges, f converges. That's the proof. Then, of course, the book says, well, if it converges, evaluate it, which kind of defeats the point a little bit. But also, it's kind of like if you ever did the thing where you look at a discriminant for a quadratic equation. If you're curious, you can use a little test to see whether there's a real solution or not. It can just save you work if there's not a real solution, but of course it doesn't save you work if there is one. So let's evaluate this. This is extra good practice. All right, so how do we do an integral like this? It's almost like arctangent, but there's an x. Let's see, u substitution's not really going to help us because there's no like x plus 4 or anything on top. Integration by parts. I don't see a trig integral. We could complete the square. We actually could complete the square. We could complete the square and get a trig integral with a trig substitution. Or not even a trig substitution. Yeah, I think you have 2 options here. Complete the square or use partial fractions. What's worse? All right, this is what happens when I'm fresh for these selected homework problems video. I haven't done 2 hours of math videos today. So I'm excited. I'm going to do both. Let's do both. Let's see, complete the square and partial fractions. Let's look. So if we complete the square, this will be the integral from 1 to infinity. I don't like writing my dx up there. There's nothing wrong with it, but this will be x squared plus 4x plus 4 minus 4. That's going to be the integral from 1 to infinity of x plus 4 squared minus 4. This is interesting. This has got to work though, right? Dx. And then we say u is x plus 4. So du is dx. We get the integral from now 5, 1 plus 4, to infinity, infinity plus 4, of 1 over u squared minus 4. Oh, it's not a plus anymore. If it were u squared plus 4, we could use arctangent. But by completing the square, it's not a plus anymore. So we can't use arctangent anymore. I think you have to use partial fractions on this one. I tried to get around it. I don't like partial fractions. And then du is dx. Yeah, I don't think there's probably anything to do here other than partial fractions. Maybe there is. If there is, you let me know. All right. So let's just use partial fractions and see what happens. So if we factor this denominator, I'm going to go off to the side. 1 over x squared plus 4x is equal to 1 over x times x plus 4. And we know from partial fractions, we have two distinct linear factors. So this will be some number over the first plus another number over the second. And then we just have to solve. So we multiply both sides of this equation, both sides of this equation by the LCD. You get 1 is equal to a times x plus 4 plus b times x. Now we can either equate coefficients or use strategic substitution. We use strategic substitution. We'd plug in x equals -4. We'd plug in x equals 0, and we get a and b. But let's look at the other way, because I don't do the other way a lot, so it's good practice. This is going to give us, let's look at the terms of x. What are the coefficients of x? 0x is on the left-hand side, ax is on the right-hand side, and bx is on the right-hand side. Now, if you look at our constants, we have a 1 on the left-hand side and a 4a on the right-hand side. That tells us that a is a quarter. And indeed, if you plugged in x equals... Wait, what happened? Yeah. If you plugged in b equals 0 here, sorry, if you plugged in x equals 0 here, you'd get that 4a is equal to 1. You'd also get the same result. So since a is a quarter, b has to be -1/4 because they have to add up to 0. So this integral is the integral from 1 to infinity of just a, which is 1 over 4 times x, plus b, which is -1 over 4 times x plus 4. All right. And now what we can do is we can use limits, improper integrals. This is the limit as b goes to infinity of the integral of 1 to b of the same guy. Take the antiderivative. Be very, very careful here. This is 1/4 x to the -1. There's a couple ways of writing this one, but its antiderivative will be 1/4 times the natural log of the absolute value of x. And the second one is -1/4 times x plus 4 to the -1. We can do a u substitution. But either way, we're going to get -1/4 natural log of the absolute value of x plus 4. Evaluated from 1 to b. Uh-oh. What's going on here? Oh, I know what's going on here. Okay, so you're going to get something really weird. As b goes to, well, I don't want to spoil it, but I already did. As b goes to infinity, well, plug in everything. 1/4 natural log of b. Don't need the absolute values. B is going off to infinity. -1/4 natural log of b plus 4. And we're subtracting that. Oh, I shouldn't have ended my brackets yet. We're subtracting by what happens when you plug in 1. 1/4 natural log of 1. Oh, that's 0. -1/4 natural log of 5. This guy is 0. And now this, again, I want to be very precise here. In the first problem, I said all that matters is this is infinity. And specifically, I implied all that mattered was this. All that matters is that the entire limit is infinity. Not just the blue part. What mattered is that this whole green part is infinity. The entire limit was infinity. It didn't matter what the other limit was. We had one limit that was infinity. Here, there are two parts, but this is the single limit. So even though natural log of b goes to infinity, we have to look at this whole green guy as a limit. Okay? And that's what we're going to do on the next page. We're going to go off to the side and look at this limit. All right? Because once we find this limit, we're just going to subtract. Actually, we're going to add, right? It's just going to be that limit, whatever that is. And we know it converges, right? Because we used a comparison test. So we know this limit will equal something. And then whatever it equals, we're adding 1/4 times the natural log of 5. Because we're subtracting a negative 1/4. Also, not only do we know it converges, we know it has to be smaller than 1. Because this function is smaller than that function, and the area under that function is exactly 1. So we know about what to expect from our answer here. So let's find out what that limit equals, fill in the blank, and then finish the problem. I actually think I know what this limit equals to. I think it's 0. But we'll see. We'll see. So natural log goes to infinity minus natural log going to infinity. Infinity minus infinity. This is an indeterminate form. Sometimes this means positive infinity. Sometimes this means 7. Sometimes this means 3. Sometimes it means 0. Sometimes it means negative infinity. Who knows? All right. And we have to use some tricks. We don't like subtraction with indeterminate forms. So sometimes with fractions, we combine the fractions. Natural logs are the same. Let's combine these. Let's get rid of that subtraction. In fact, let's factor out a 1/4 from the whole limit. Then we get the natural log of b minus the natural log of b plus 4. How can we combine natural logs with subtraction? We can divide their insides. Remember your properties of natural log. This is just the limit of the natural log of b divided by b plus 4. And now what's happening? Now, you may or may not remember from Calc 1, because there's a lot of limits, so you're going to have to review your Calc 1. You may or may not remember that if we have function composition, which we do here, some function, and there's another function inside of it, if the outside function's continuous, the limit can go inside. And that's exactly what we have here. So this is 1/4 times the natural log of the limit as b goes to infinity of b over b plus 4. As b gets infinitely big, what is the limit of this rational function? So it's a rational function, which means a polynomial over a polynomial. If the degree on the top is bigger, it's infinity. Degree on the bottom is bigger, it's 0. If the degree is the same, which we have, linear function on the top and the bottom, linear function of b anyway, then we just look at the coefficients, the leading coefficients. So we're going to get that this limit is 1 divided by 1. This limit's 1. So that leaves us with 1/4 times ln of 1. What's the natural log of 1? 0. All right, the 0 looks really weird when I write it like that. I gave myself too much space. So this integral really does just converge to 1/4 natural log of 5. This better be a positive number, and it better be smaller than 1. Thank goodness. You could also check your answer. Integral from 1 to infinity of 1 divided by x squared plus 4x. Hey, look at that. We're done. Let's do another problem. 389. I was worried I didn't have enough problems in this section, but, well, they're taking time. Did I say 381? 389. Evaluate the improper integrals. Each of these has an infinite discontinuity, either at an endpoint or at an interior point. Integral from 0 to 4 of x ln of 4x. And again, it's very important that you acknowledge that there's a discontinuity. Otherwise, when you do this integral, you're going to get some funny business most of the time, and some of the time you'll escape. But let's not risk it, right? Better safe than sorry. Let's do this proper. So before we even worry about this, well, let's do the hard part first. Let's do the 3.7 part first, and then we're done with 3.7. This is the limit as a goes to 0 from the right. 0 is where the problem is, because we have an asymptote. Actually, we don't have an asymptote in this case. Natural log would have an asymptote, but anyway, I don't want to spoil it for you. But this integrand is not defined when x is 0. So we're going to take a limit. Everywhere else looks fine. And again, we want to approach from the inside, so that means it's a limit as a goes to 0 from the right. A to 4, I don't know why I'm in red. Let's switch back. X times the natural log of 4x dx. Now we need this antiderivative. Now, nobody likes writing a limit 50 million times, myself included. So let's go off to the side to find this antiderivative. This is going to require integration by parts. Let's let this be our u, and this be our du, or our dv. The u is natural log of 4x. Du is 1 over 4x times the derivative of the inside, dx. Oh, du is just 1 over x dx. dv is x dx. So v is 1/2 x squared. So the integral of u dv is u times v, which is 1/2 x squared ln of 4x, minus the integral of v du, 1/2 x squared times 1 over x dx. We can keep simplifying. 1/2 x squared ln of 4x. Really should have given myself more room here. Minus 1/2 the integral of just x dx. This is 1/2 x squared ln of 4x. We've done similar integrals to this before. Minus 1/4 x squared plus c. That's our antiderivative. So we can resume our problem. The limit as a goes to 0 from the right of the antiderivative, which is 1/2 x squared ln of 4x. Minus 1/4 x squared, we don't need the plus c. Evaluated from a to 4, and then we can plug in. As a side note, we can't use the fundamental theorem of calculus on here because it's not defined from 0 to 4. But we can use the fundamental theorem of calculus here because a is some number that's bigger than 0. A is getting really, really close to 0, but it's always bigger. So this will be 1/2 times 4 squared times the natural log of 4 times 4 minus 1/4 times 4 squared. And then subtract what happens when we plug in a. 1/2 a squared, natural log of 4a, minus 1/4 a squared. So this guy, as a goes to 0, is 0. The second one, we've done something similar in the videos. Let's look at it. Let's look at this limit in the next page. 1/2 a squared. Limit as a goes to 0 from the right of 1/2 a squared natural log of 4a, right? I always copy things wrong. Well, this is the form 0 times infinity, or negative infinity, because this is going off to negative infinity, this is going off to 0, this is an indeterminate form. If we had subtraction, we need to combine them. If it's multiplication, that's also not good for indeterminate forms. We really want division for indeterminate forms. So we need to write this as a fraction. Let's factor the 1/2 out in front. And then again, we have two choices. This is the better choice. Again, this is equal to each other. Dividing by 1 over a squared is the same as multiplying by its reciprocal, just a squared. Or you could flip the a squared in the natural log of 4a, but that won't be good. And now, as we're going to 0 from the right, now we have negative infinity over positive infinity. This is an indeterminate form that we can directly apply L'Hopital's rule to. So we take the derivative at the top and we take the derivative of the bottom. We already showed that this derivative, now specifically we're taking the derivative with respect to a here, because these functions are with respect to a. You can put it in terms of x if you'd like. The derivative of that top with respect to a, we already calculated it. It was 1 over a. And the bottom will be negative 1 over a cubed. Sorry, negative 2, 1 over a cubed from the power rule. And then we can just simplify. Right? This is 1 over a times the reciprocal. The reciprocal is a cubed over negative 2. Well, that's 1/2. Limit as a goes to 0 from the right. Let's pretend that's a 0 here, and I didn't write it wrong. Let's see, well, this a cancels, one of these cancels. We're left with a squared over negative 2. Oh, this limit goes to 0. So this green guy is just 0. Oh, so this whole second part of the limit is 0. We're just left with the first part. 1/2 of times 16 is 8. ln of 16 minus 4. Now I would ask that you simplify this. Okay, does the book simplify it? The book doesn't simplify it. That makes me sad. I would ask that you simplify this. This is the book's answer. But remember that 16 is 2 to the 4th power, and you can bring exponents out in front, right? The natural log of 2 to the 4th power is 4 ln 2. So with an 8 in front, 8 times 4 is 32. 32 ln 2 minus 4, I think is a lot cleaner. But it is what it is. Let me know if you have any questions about this one. And let's do the last one. 391. So I just chose this one because I assigned it on the homework problems and I saw in parentheses, be careful. All right, so let's see what it is. Let's see if I fall for the trap. I don't know what the trap is, but it wants you to be careful. Evaluate the integral from 0.5 to 1. I'm going to write 0.5 as a half. I might regret it. Of dx over the square root of 1 minus x squared. All right. Okay, so looking at this looks like arcsine, right? The antiderivative of 1 over the square root of 1 minus x squared dx is arcsine of x, no? They said be careful, so I'm checking my answer. Integrals. Hold on. 1 over the square root of 1 minus x squared is indeed arcsine. The thing is, right, that we have to be careful because this function is not defined on the interval from 1/2 to 1. It's defined at a half, no problem, and it's defined everywhere up until 1, but at 1, it's no longer defined. And then bigger than 1, it's no longer defined, but we don't have to worry about that. So this is going to equal the limit, b approaches 1 from the left, integral from 1/2 to b of this guy, which is the limit as b approaches 1 from the left, of its antiderivative, which is arcsine of x from 1/2 to b. Now we can just evaluate. I'm wondering if I fell in the trap. I'm nervous. Arcsine of b minus arcsine of 1/2. And we have to evaluate this. So remember, these are the question. The sine of what angle is equal to b? And again, specifically, we know that the domain of arcsine is negative pi over 2 to pi over 2. And then we have another question, sine of what angle is equal to 1/2, where again, x is in that same region. So we're going to get, it's a positive ratio, so it'll be in the first quadrant. These are 2 quadrants, first and fourth. And 30 degrees, pi over 6. This is pi over 6. Okay, and as b is going to 1 from the left, what is this going to be? All right. So I think there's a quick way of doing it, but I'm going to not do it the quick way because they said be careful. All right. So sine of x equaling b means that x, and again, b is going to 1. It's a positive number, so we can draw this in the positive quadrant. Sine of x is opposite over hypotenuse. That's sine of x equals b. And what happens is b is going to 1. What is x doing? As b is going to 1, this is going to 0. All right, this is the square root of 1 minus b squared. As b is going to 1, this is going to 0. So that angle is going to pi over 2. So our answer is just pi over 2 minus pi over 6. So that's 3 pi over 6. Minus 1 pi over 6. That's 2 pi over 6. That's pi over 3. And that's the answer. Well, I wanted it rounded to 3 decimal places, right? Pi over 3 is 1.047, which is what the book has. Huh. Why did they say be careful? I was so worried. Maybe they just wanted you to recognize that this is an improper integral. Because this is one of the, how I said that if you don't write this limit, sometimes you'll get the wrong answer and sometimes you'll get the right answer, but it's best, to play it safe. But this is one of those situations that you get the right answer even if you don't do it right. So I don't really know what they're going for with this wording. It seems like a pretty basic problem. Let me know if I missed anything. But here we go. Arcsine. Let me know if you have any questions and have a great day.